Hello students, in this video we'll discuss arc length parameterization of a curve. If we're given a curve, r of t, which is f of t I hat plus g of t j hat plus h of t k hat, for t between negative infinity and infinity, we can perform ordinary calculus on this curve. We can compute the derivative r prime of t as the derivative of each individual component, as f prime of t I hat plus g prime of t j hat plus h prime of t k hat. So, to perform calculus on a curve, we perform calculus on each individual component. Then, from this, we can define the speed of a curve, the speed of the curve r of t is the length of the derivative of the curve, the magnitude of the derivative. And so let's think about this for a minute. So geometrically, of course, what do we have? If we're given some curve in space, so if this is my x, y, and z, let's say it's a three-dimensional or space curve, x, y, and z. There's my curve. So my curve is moving like this. Now, what will this derivative represent? Well, what will happen is if this is my r of t, and this is my r of t plus h, then we draw the vector to r of t, vector r of t minus h, then this secant vector over here is r of t plus h minus r of t. And so we can see that as if I divide this quantity, this difference by h, and let h go to 0, that I'll get a tangent vector. So this has an interpretation that this is also the limit as h goes to 0 of r of t plus h minus r of t over h, and this is a tangent vector. Or this tangent vector also represents the velocity vector of the curve. And so that is a way of measuring speed. And so for example, if you look at this curve over here, r of t, which is cosine of t I hat plus sine of t j hat for t between 0 and 2 pi. Then r prime of t, the derivative of this, will be negative sine of t I hat plus cosine of t j hat. And let's compute the magnitude of this vector. The magnitude of r prime of t is the square root of negative sine squared plus cosine squared, and that's equal to 1. So this curve over here is called a unit speed curve. Unit speed, because the speed of the curve is always equal to 1. We can look at a different curve, different representation of the curve. If I look at r2 of t, which is the cosine of 2t I hat plus the sine of 2t j hat, then the derivative of this curve, the velocity vector for this curve, is going to be negative 2 sine of 2t I hat plus 2 cosine of 2t j hat. And we can check, we call this r2, that the speed of this curve, r2, is equal to 2. So this curve has 2 speed. The speed is equal to 2. Let's look at one more curve over here. Let's look at this final curve, r3. So both these curves have constant speed. So the speed here is constant. And over here, the speed is constant. Constant speed of 1, constant speed of 2. And if I look at this curve over here, r3 of t, which is the cosine of t squared I hat plus the sine of t squared j hat. That's also a unit circle. But if I look at the derivative of this curve, r3 prime of t, we'll have a 2t with a negative sine of t squared I hat plus 2t cosine of t squared j hat. And so if we compute the length of this vector over here as an exercise, you can compute the length of this vector will be to absolute value t. So this curve over here, this R3 curve, is still parameterizing the unit circle. However, the speed at which it traces out the unit circle is growing linearly. It's growing as t grows. It's growing at a rate of 2t. So although there are different ways to parameterize the unit circle, R1, R2, and R3, all give parameterizations of the unit circle, they all have different speeds. We will see that we want like a methodology for figuring out how to compute a curve that has unit speed as a way of standardizing the choice of curves we have and allowing us to compute quantities associated to a curve, such as curvature and torsion. Thank you very much.